Okay, today we're going to continue our talk about virtual memory. Um, a lot of what we're doing in the virtual memory is very similar to what we were doing with just looking at main memory in general, especially paging. So paging and virtual memory are usually very, very intertwined because they kind of each use the features of each other to get better performance or simulate more memory. So we talked briefly about this idea of a page fault. Okay, so a page fault is what happens when we attempt to reference memory that's not located in physical memory. We attempt to locate an address that falls onto a page that's not in physical memory. Okay, there's two reasons that this might happen, that we might reference an address that's not in physical memory. Anybody know what those two reasons are? Well, what's that? I don't know how. Well, we could run out of memory, but really the page fault didn't happen because we already ran out of memory. The page fault happened because it's not there. So, running out of virtual memory, if we give each process a view of 4 gigs, whether we have it or not is a question. So that's what might be meant by running out of virtual memory. But they still are supposed to be able to get to 4 gigs of memory, right? So, but one of the main reasons that we page fault is just normal, okay? We haven't loaded it into memory yet. So we have a page that we haven't put into a frame so that we can use it. So a page fault is normal in that case, okay? A page fault is kind of telling the operating system, hey, I wanted to use this address, but you don't have it in memory. Can you go fetch it from disk, put it into memory so that I can start using it? Or can you allocate it to me and give me some free memory so I can start using it? Okay? That's one reason for a page fault, is we referenced it and the operating system hasn't allocated a frame to us, or it hasn't loaded it from disk, or it's just not available in physical memory. Okay? Another reason is because we're referencing an address that we're not supposed to be able to reference. Right? If I try to go beyond, like, for example, the 4 gig that I was given, then which you can't really do because you can't create that address, but if you try to reference something you're not supposed to reference, that's also a page fault because it's not loaded into memory because you're not supposed to have it, right? So it shouldn't be loaded into memory. So there's two reasons that we might page fault. But one thing I want to emphasize is that page faults happen through normal use. The first time we encounter a page, right, an address that falls in a particular page, the operating system will page fault in these demand paging systems. Okay, will page fault, lets the operating system know it's not in memory. It will go get it, put it into memory, and then restart the instruction. Okay, so and these are some of the steps that happen when a page fault occurs. Okay, so because we have to do these additional steps of going and getting the memory page and putting it into memory and getting it ready for use and restarting the instruction, we take a performance hit, right? So all of that overhead of getting the page from disk, putting it in, and restarting the instruction, that is the overhead of page faulting. Okay. So again, if we do a calculation similar to what we saw before with some of these other, with some of the other techniques, like using the TLB when doing paging, and also this happens with cache, but we get some sort of rate at which we do this undesirable thing of taking on page faulting overhead. So if the page fault, if we take one of these to be the page fault rate, P, right, then 1 minus P would be the rate at which we go to access memory addresses and they're there, right? We don't page fault, okay? So we do 1 minus P times the memory access. That would be a normal access without a page fault. Everything else, P, right, takes on all of the overhead of a page fault, right? Probably in addition to the memory access as well. But this stuff's so big you don't even really need to worry about that. So what they're calculating here is the effective access time. So if we were to look at, on average, how long it takes us to get to a particular, a given memory address, the effective access time is the average that we take on, which is a combination of our very slow access time of loading a page into memory and then accessing it, plus our very fast accessing a page that's already there and just doing the memory reference. Okay? So, this kind of measurement can help us determine whether our paging is good or bad. Okay? Because we'll see that there are other factors, and what we're going to go over today are things like page replacement algorithms. And to compare these, you'd look at something like the effective access time. If one provides you with a quicker effective access time, most of the time you'd say, this is a better system than this other one. Okay, so they give us an example here, right, using some kind of ballpark numbers of how long this kind of thing takes. Notice the scale at which these two numbers are, right? If 1 minus P times this, what does this represent? Regular what? Memory access time, right? So this is memory access, this 1 minus P is the memory access time when the page is available. We do not page fault. Notice we have a small number, 200, right? And then if you look over on the other side, right, where we have P, which is a page fault happened, notice 8 milliseconds as opposed to 200 nanoseconds, okay? So very, very big number, 8 million versus 200, okay? So obviously this impact of page faulting is very, very large. So in order to make our effective access time acceptable, what do we want to do? Notice they reduce it down to 200 plus P times this big number. So what would reduce the access time? Right, so we need to make this P very, very small, which is the page fault rate. How often we page fault compared to how often we don't. And notice how small it has to be, right? If we want to get 8 million down to the scale of 200, P needs to be very, very small, okay? So they're showing here that if one access out of 1,000, right? So what's that, 0.1% of the time if we page fault, right? Our effective access time is 8.2 microseconds. What was our effective access time with no page faults? It was 200 nanoseconds, right? So that's letting you know that this is a big deal, the number of page faults we have. So a lot of designing these systems is obviously surrounding this making P very small. In other words, not page faulting a lot. Okay? But we did some examples the other day where we walked through running a program with different loops and things, right? And we saw that how we decide to page in, we change the number of page faults we make, right? But then we also have this minimum amount of page faults that we have to kind of take on, right? If we were to, if we were to run through all the pages, we at least have to load those pages, okay? And you need to keep that in mind when comparing these types of things, like looking at page faults and things like that, right? Because you kind of can't count the first page fault for any given page. Why do you think I say that? What's that? It's always a fault in our demand page system. But it's also always it's not a fault in other systems. But what I'm saying is if I don't use demand paging, right? Demand paging says when I access a page, I'm going to go load it. Okay? What's the other alternative to that? The whole program, right? Or whatever I'm going to be accessing. You just pop it all in memory. And that's what we've been kind of looking at, how we've been looking at memory up until now. Is just I take the program, I put it in memory, right? So, if I have a program, and I'm just going to put these lines here because that's how many pages it would take. Okay, if I put some lines on there, that would be the pages. But if we're using our other system where we just load the program into memory, right? We'd have memory, and then we take this whole thing and pop it into main memory, and then we'd start executing instructions, and we can jump and loop or whatever. Okay? So, in this case, if I load everything up and start walking through it, how many page faults will I have? None, right? I wouldn't have any page faults because I could never run into a location that I haven't loaded, right? If I do this with a paging system, I'd start attempting to run the first few instructions and I'd page fault. Then I'd load it up. Okay, so I've had one page fault. And let's say I get to the next page, I'd load it up, right? And then I'd run, and then I'd load it up. So I've taken 3 page faults here. And all we did was just run directly through the program. Okay? So I've taken 3 page faults with my demand paging system. And with my other system, I took 0 page faults. Okay? So if we just look at it in this naive way of this formula, one of them took 3 times 200, right, for accessing those pages. Another one took 3 times 8 million. Right? But how do the overall run times of these programs compare? Is one really, millions of times faster than the other? See, no. I know the numbers work out. I mean, the formula is saying that one took 8 million times 300, and the other one took 200 times. But what did I ask you? Like, just overall, how did they run? Okay, so no. Why not? Because I asked. I wouldn't ask if it was exactly what the formula said. Right? But why? I mean, something's hidden, right? Some cost is hidden. Why is this 8 million and the other one 200? Stuff like disk, right? Like going down a disk and loading up page. So, if loading the whole thing is looking like 3 times 200, and the other one looks like 3 times 8 million, right? The 8 million comes from loading from disk. So what did I hide from you? For loading everything at once, right? Where did I hide it? I hid it when I said I load up this whole program into memory. What does that entail? That means getting all of the program off of disk and put into memory. How long does that take? It takes on the scale of this 8 million. It's not as much because there's more going on in this 8 million than just loading it from disk. But the scale is of this scale. So what's the difference? Well, loading everything into memory, you pay the costs up front. Right? Demand paging, you pay it as you go. The loading it all into memory will be faster. Well, if we access every page. What is the trade-off? Why would we do this demand paging if we have a faster way?
Probably you don't need some part of it.
That's one case. One case is where the performance of demand paging it actually pays off. And the performance is when you don't access every page. A good example is one from the book where they say you have a large program, right? But what if the first page of that program is printing out a menu saying which part of the program do you want to use? And each of these other pages might be just a part of that program, right? You can actually get better performance overall if you just choose one of the options and you don't end up using any of the other options because you load 2 pages, whereas loading the whole program into memory, you'd load everything. So that's one case where why we would do this. What are some others? Well, if we're accessing every page, it wouldn't. Right? Because there's no getting around that if we have a long program, we'll have to eventually load every page into memory if we're going to touch every page. Right? There's no getting around that. But loading everything at once is less overhead than loading it as you go, because there's a lot more that goes on if you load it as you go. Right? Doing stuff in batches usually is more efficient because you don't switch gears and do something else.
When you say load it all into memory, do you mean is that a contiguous block or is it?
Normally, those are some of the techniques we've seen is loading a big contiguous block. So what would one of the advantages of this demand paging system be? Right, you wouldn't have to have such a big block, and on demand paging especially, you don't even need to have enough memory, right? If we're using this virtual memory idea, right? You could be running programs that you can't fit into memory, whereas loading it all at once, you can't do that. So there are trade-offs, right? There's the idea that we don't need, we can use these pages a little bit more, with a little more flexibility, right? But we do sacrifice. We sacrifice mainly performance. But I just want to make sure you're clear on the fact that there's other factors than just, whenever you see a formula, you should say, okay, where are all these numbers coming from, right? So I just want everybody to kind of realize that this, big number that you see in the formula for paging, a lot of that number is actually paid by other systems just at different points. Okay, you need to. Keep that in mind. Is that when it's all said and done, when you're working with operating systems or memory, virtual memory, things like that. When it's all said and done, everything needs to end up in memory somewhere so that a CPU can look at it. Right? If we're running instructions, it ends up in memory somehow. And a lot of this stuff is really just how are we going to have it end up in memory, and what are the trade-offs with that?
I understand the second part you said with the contiguous block. I don't understand. What do you mean by that? That problem one reason. You just said the contiguous block to put on the memory.
Right.
From that point, I understand.
What do you mean?
Like I said, one reason that probably you don't need to
load all the pages. Okay.
Then we said that there's contiguous memory reason.
Right. The thing is if I have a program that's the size of this left block here, right, and I have a memory that's the size of the big block on the right, right? If I allocate that kind of memory allocated, I can't run this program if I'm using contiguous allocation. Right? I can't because there's no block big enough to fit the whole thing. mean, if these are page sizes like that, I can run it. Right? Even more so, if I'm using virtual memory and paging, I can still run this program. How would I run it?
That's paging system, and that's not each page.
They can that frame can fit each of the pages. But how would you execute it? That doesn't change the fact that I need 3 frames, right? Just use the same frame. I need 3 frames.
Yes.
I just use the same one for each of them, right? I'll load page 1 or page 0, run what I need to run on it. When I trip off the end of it and go to page 1, I'll erase that. Grab this other one, put it in there, start running. So that's a kind of trade-off, right? The contiguous memory allocation, we didn't have that possibility. So in other words, I mean, all of this is a question of why would anyone pay this kind of price? You know, the 8 million when I was getting it for 200 before. You know, there has to be a very, very compelling reason to do this. Right? Stuff like that is the compelling reason.
On the formula,
Mm-hmm.
it took into account swapping out.
Mm-hmm.
Do you automatically swap out when the page is done?
No, right? So like if we don't alter this program, when this thing goes away, we don't actually have to write it back down to this. Right? So and I mean that's a big point too, is that number is a lot of different numbers inside it. So this is kind of here's a ballpark of your effective access time, right? But a more detailed formula would take into account that no, we're not doing that for each page fault that we have. Okay? Here's an interesting question. At least to me it is. All right? What do you think the formula would look like if we distinguish between pages we have to swap out and those we don't?
Do that faster, you don't have to swap out, right?
Right. Yeah, the formula would be a smaller number. But what would the formula look like? How do you think you design that formula? Yeah, this is better. Okay, so what we're saying is, some of them don't need this. Right? Some of them don't need the swap page out portion. Okay? So let me get started. We have page fault overhead will be, let's say, we have fault with swap out. Right? We have fault without swap out. Right? And then we have just memory access. These are times. These are our number. Right? This is 8 million. This is less than 8 million. Right? A little bit less than 8 million. This is 200. All right.
That's part of the swap out. So
We don't know the number. I gave you you can plug in the number when you find out how long one takes over. I'm not telling you tell me how long it takes with swap out versus not swap out, because you can't know that. Right? Unless I gave you the speed of the disk, the speed of the memory, how big the blocks are, all that stuff. I've given you the number. The number is those words. Fault without swap. That's a number. Don't worry what the number is. What I'm asking you for is what is the formula? Someone should at least be throwing out ideas, right? At least give us the same a formula. Okay, so somebody throw out 1 minus p. Where do you think we would put 1 minus p? Okay. The answer is 1 minus p stays at the same spot. Wait, what? Times where? I have 1 minus p times memory access. That's all I have so far. Plus p
minus swap time.
Plus p minus swap time? What's swap time?
If we do without swap, then that time should be
Okay, so
taken out from the p.
what symbol do you want me to put after the p? What? Q. Okay.
Minus q.
Huh?
P minus q.
And Q is
Q is swap time.
swap time.
Yeah, swap in and out time is included in
This is swap in and out time. This right here. So you want me to say p minus that?
Oh no, then it's only p. And next part will be then p minus p. Here.
Do you want this to be multiplied? Multiply the two?
So that's it.
Does fault with swap out include all 4 of those terms?
Everything. It's the old number we had for
Yeah, that
it.
should be multiplied. The fault with swap out.
Okay, so p times
That.
fault with swap out. Okay.
And this side should be p minus q
No.
times.
Okay. Everybody's just throwing out. What do I put next? Do you want a multiply? Do you want minus
P
minus p
times
times this? It's not good. But at least it's a formula. No. Why not? What is p? Yeah. This is how many times a page fault. For some reason we're subtracting out just an arbitrary amount. I mean, we've taken. You know what's left here? The time it takes to what's left in this p times fault with swap out minus p times fault without swap out. You know what that is?
Why don't you get rid of the first p?
No. That's what that is. Right? If I were to take the p out. Right? And then so that would be fault with swap minus fault without swap is swap. So this is p times swap out. No good. Yeah.
So why don't you get rid of that first p over here? Plus p.
This right here? Done.
Because you're only even counting the fault without swapping, right?
No, we're counting all the faults.
Well, that's wasting time, right?
What's wasting time?
Without swapping, right? Well, not really.
Without swapping is better because it's a smaller number.
Wouldn't you?
I'm going to give you a hint. You guys are missing a number.
The swap out time.
No. I've given you the swap out time, and I just showed you how you could get the swap out time. You take fault with swap out minus fault without swap out, and that will be your swap out time. You're missing a number. You're missing a variable. No. That's included in both. You don't need to know what the restart overhead is. What number are you missing? It follows the same pattern that we've seen in all of these formulae. Okay. I gave you this formula and I said P is how many times we page fault. 1 minus P is how many times we don't page fault. So, if I say, what did we do when we did the TLB? Right? I gave you P is how many times we get to use the TLB. 1 minus P is how many times we don't get to use the TLB. Caching. Right? P is how many times what you're looking for in cache is there. 1 minus P is how many times it's not. What am I getting at? You're missing something like P. What something like P are we talking about here? Where is there a difference in sometimes we get lucky, sometimes we don't, that we've added to this formula? What did we add to this formula? First of all, from here to there, what did we add? Fault without swap out. This is what is new. How often does this occur? We have no idea. You have no idea. You have no idea. There's no way to tell. So, when we have no way to tell, what should we use? We should use a variable. Let's use Q. Okay? So, we're going to create a variable Q. What does Q represent? Use words like that. Okay, so Q is how often we get a page fault without swap, with no need to swap. No. All the other times would be without, right? So 1 minus Q. We're going to do a sub-formula, okay? So if 1 minus Q is how often we fault without swap out, Q is how often we do it without, right? With swap out, 1 minus Q. Without swap out, Q. Okay? How often do we do all of this? P, right? This whole thing we do at the rate of P, right? Everything else is 1 minus P. Inside this rate P, Q times, we don't need to swap. 1 minus Q times we do. So, how do we do it? Well, we've got Q, right? 1 minus Q, right? And this whole thing, P.
What's the variable in front of the fault?
Huh?
What's the variable in front of the fault for swap out?
P. Oh wait, this is 1 minus Q. This is P. So it ends up being P minus Q here, but you need to make sure that's PQ. So does everybody see how we built kind of a similar formula to what we're used to inside? And then we just took that whole value and said, okay, P. Because what we were trying to find is, sometimes we get to not swap out and sometimes we have to, right? So what we were trying to say is, on average, how long does it take us to swap out? I mean, how long does it take us to page fault? So on average, we get our rate, 1 minus the rate, combine it, and then that's our average. So this number that comes out, this whole number inside the brackets, okay? This will be, with P in front, it'll be P times a number slightly smaller, a number smaller than fault with swap out. And without swap out. Okay? It'll be a combined number of both with and without swap out. Right? Somewhere in the ballpark. Greater than this, but smaller than this. Sorry, greater than without swap out and smaller than with swap out. This number right here. Okay? How do we find that number? By using this Q as some sort of rate at which we get to do the faster one as opposed to the slower. Okay? That's a good, I mean, thinking like this is a good exercise. This idea of how often do I do the good thing versus the bad thing, and putting in a rate there so that we can kind of see if there's any patterns and whatnot. Or how low do we need to get the rate, right? Okay. But this type of thing is very, very useful. Thinking like this. This happens a lot in a lot of architecture and those kinds of subjects in computer science. Because architecture is all about balancing these needs. Okay? So, we will now we understand the issues that are kind of surrounding a page fault, right? We take on a performance hit, it gives us a lot of flexibility. Yeah.
How does really the queue ever in reality be defined?
By watching programs run. If you have this feature of you don't have to write pages back sometimes, right, for pages that haven't been altered, we're going to look a little bit at that. But if you have that feature, the way you can tell how often it happens is running programs and seeing how often they happen. You can't define how often it will happen, right? Unless you're going to define what kind of programs your users can run. What kind of program would Q be high for? No. What type of program would Q be high for? I/O access has nothing to do with it. What is Q? The rate at which we can swap something out without having to copy it back to disk. We can just throw the page away. No. Because the program with the menu example is never swapping something in. It's a program with a lot of code as opposed to a lot of data. Why do I say that? Why would Q be high, or something with a lot of data that you don't alter? Although not so much, but yeah, something like that. Why do I say that? When do we have to swap something back out to disk? Yes, I mean, all pages you probably want later. But when do we have to copy it back to disk? Oh yeah, the time that you do it is when you want to use the space up. But what I'm saying is as opposed to not copying it back to disk. When would you be free not to copy it back to disk? In other words, just throw the page away. When you have a copy somewhere else. The what? No. If you're running a program, you're welcome to use any piece of memory that you had again.
But is there a way of determining that maybe this portion will never be used again?
No. There's no way to find out that it'll never be used again except by running. One tiny little jump instruction could make it be used again. Okay. We know we can throw it away if we have a copy somewhere else, right? Which is things like program code or something that we've already swapped out to disk and we haven't erased it. When do we know we can't just throw something away? When it's holding things like data that doesn't exist anywhere else. If you're doing a calculation and you're storing the results in memory, throwing that memory away would be bad. But if you need that frame, you need to take it out of memory, so you have to copy it back, right? Okay, so when would Q be high? When you can throw a lot of pages away. In other words, you have a copy of it somewhere else, and you don't need to copy it back to disk. So the example I said was a program that has a lot of code as opposed to a lot of data, right? Because code we have on disk already, because that's how we loaded the program to begin with. So if we toss pages away, that's fine, because we can just load them back from disk. Q would be high. Q would be low. We have a lot of data that we're altering. Why? Because every time we need the frame where that data is, we have to copy it back to disk. 1 minus Q. Right? Okay, so given that, you can see how we can't determine Q. Right? We can't analyze Q to say that this will happen. Right? Only through things like simulation or watching, programs run on a system can we know what is Q likely to be. Okay? So, process creation. Okay? The main concept we want to pull out of here is copy on write. Okay? Copy on write. We saw before that what happens when we use a call to fork? What's that? Copy the what? Right. We copy the whole memory, right? The code, the variables, right? So what we do when we fork is the parent makes a duplicate of itself, and that becomes the child. Okay? So, copy on write is a little trick where there's a tricky way to copy memory. What is memory to a process? A process has logical memory. Right. It is a place. It's a place to store things like variables and your program code, right? But what does it look like to a process? Flat memory address, memory space, right? So we'll have just a big area, right, that goes from 0 to some, to some limit, right? And it's just addresses from 0 to a limit. Okay? Now, do we give this process that much memory? That's all we've been talking about, right? Is you don't have to give it all the memory. Okay? So instead, what we do is we have frames. This physical memory. Okay? And what we do is we say, okay, you have pages. They fit in these little frames. And what else do I need? So I got pages, I got frames. Table, what kind of table? Page table, right? So I'll make a page table, which is like my the same as my pages, right? And I'll number them, right? And then what will I do? I'll map the entries in the page table to frames, right? So then I'll have different pages. Right? That map my pages to frames. Okay. I fork. So fork means create another process that's just like mine. So, child. What do you think is a tricky way to copy that child? Same page table, right? Redo the page table. So what you do is, the trick is, you just make a copy of the page table. That way, when we're running along and we're swapping between a parent and a child, they can just be looking at the same frames in memory because they have the same data. Okay? But when does the problem occur? What do we notice in our fork examples? Right. They could be doing two different things, right? So I could alter, for example, a variable, right? And then when we print that variable, we saw two different things, depending on whether we were the parent or the child. Okay. So, where does the problem occur now?
It's going to assume that they're the same variable, and when you change it in one, it's changing the other.
The other one will see it, right? Because if I have a variable is nothing but a location in memory. So let's say this variable, this counter or whatever, right, that we're looking at. Let's say it's contained on page 1. Somewhere in page 1. So in page 1, there's a little slot that has a variable in it. So where is that in memory? Frame 3, 0, 1, 2, 3. Right? Somewhere in here, there's a little slot that has a variable. When the child process goes to page 1 and looks at that variable, notice it is the same physical spot. So, if the child reads it and the parent has altered it, the child will see the altered value. We know this is not the case, right? We've looked at fork and it doesn't work like that. So, our trick was really nice. Why was our trick nice of just duplicating the page table? What benefit did we gain? Right. So one is we're using half the space. Right? The physical memory, we don't need actual physical memory to contain the copy. The other thing is that we didn't actually spend any time copying anything. We had to set up a page table anyway, right? By just putting in the same entries. We didn't copy a single block of memory yet. So that's really good. But we've run into a problem, right? Now, when we alter different variables, they end up getting altered in both. So, copy on write to the rescue. Okay? Copy on write means, what do you think it means? Copy what on the fly?
One program writes.
What variables?
Like if the variables are shared between the parent and the child, like one writes it, there'll be a different thing.
That's the key, right? When you write to a variable, when you write to a memory location, that's when you copy on the fly, right? So copy on write means if something's written, copy it first. Don't write on a page that's shared. So what they're showing here, right? We have two processes pointing to the same physical memory. Okay? Process 1 wants to write to page C. Okay? So what it will do is, this diagram is actually not the right diagram. Okay? Your book has the right diagram. What you should see here is this. Let's put our pages in the frames, okay? So, page 0 is in frame 2. 0, 1, 2. This is page 0. Page 1 is in frame 3. Page 2 is in frame 1. Right? Page 3 is in frame 0. And page 4 is in frame 4. Oh, we have the perfect amount of frames. Okay? So, that's how our memory looks. Okay? Child wants to go alter this little variable that's on page 1. Okay? So, if we're going to copy on write, what do? Child goes to page 1 to write to it. That's contained in frame 3. Okay. No, you're not allowed to write to it. Why? Because we're sharing it with the parent. So what do? I copy. What I do is I put it somewhere else. put it in frame 5. I put the child's version of page 1. And then I write it. Then I alter my variable in here, x or whatever.
So basically, the shared memory and read-only.
Until you try to write it. See, that's the thing, is they are welcome to write to it. Okay? So read-only would imply that they're not allowed to do anything with it, which some pages are. If something's read-only, you're golden. You can point as many things as you want to it. Okay? This is a trick with read-write memory that you can do, where you get the benefits of the read-only until you need to write.
Like that actual physical space, you can only read with
Yes. But see, notice that we made a copy for the child before we read. You know, depending on how the operating system handles it, it could also make a copy for the parent if it tried to write it. Right? Or the trick is that we are writing. But the thing is you need to just make sure that if you're the first one to write, you need to make a copy. Because see, now the parent is free to write to it. Because it's the last one looking at that page. Depending on the scheme, probably would not. That's a redundant copy. But see, then it gets difficult. What if you have 10 different children? So you have to do some sort of tracking of who's looking at whose frames. Right? But I mean, all you have to do is check, are you the only person looking at the frame that you can alter? Okay? So that's a neat trick. Notice we're still reusing memory where we can, right? We still got that big performance boost from not having to copy a bunch of memory. Now we only copied where we altered it, right? And there's a good chance that a lot of these other pages that are in these other frames we won't ever change, like the code and everything. Okay, so that's what the picture looks like. Not like this. The one in the slides is wrong, but the picture in your book is right. They have a better picture of this phenomenon. Okay. If you were to, you'd need another copy of page C at the bottom of this diagram, and then the arrow gets moved to that copy of C. Okay. So that is a nifty trick that you can do with this virtual memory idea. Okay. What happens if there is no free frame? Well, we need to replace a frame. Okay. So what we've been looking at is this idea of when we need a page, when we need to put a page in memory, we've been assuming that we have a place to put it. Okay? Virtual memory, one of the biggest kind of areas where you can tweak virtual memory is in choosing which frames to overwrite or free up so that you can put pages in them. Okay? Typically, we'll use some sort of page replacement algorithm or strategy. Okay? We want to minimize the number of page faults because we've seen from our access formulas and everything like that is that if we reduce the page faults, we increase the performance of the overall performance of the system. Okay? What are we trying to approach? What is the ideal performance of our system? Effective access time equal to memory access time, right? We can't reach that, right? We at least need a few page faults, but the closer we get to that, the better our system is. How do we get close to that? Reduce the number of page faults. Okay? So, typically what you'll do for page replacement is you need to make sure we need to make sure that our routine for replacing pages, or what happens during the overall page fault, we need to make that as small as possible. We need to make that as little as possible. Okay, we need to reduce the number of page faults. Okay, Use a modify bit to reduce the overhead of page transfers, right? Only modified pages are written to disk, okay? This is exactly what we calculated out by saying some of the pages we don't have to write back to disk, right? Our new formula is looking at this second bullet, okay? Use a dirty bit to say that a page has been modified. So if your page is clean, you can just throw it out. Why? Because you have a copy of it somewhere else. If it's dirty, before you take this page out, you're going to need to copy it to disk or update its copy on disk so that we have the new data in there. Okay? Page replacement completes separation between logical memory and physical memory. Okay? What they're saying here is that now you are no longer tied to the physical memory for what kind of logical memory space you can provide programs, right? We already saw kind of a rudimentary example of we had a program that was 3 pages, but even if we only had 1 frame, we could still run it. In other words, we're not required to have physical memory anywhere near what our virtual memory is. Okay, which is big. Okay, so just to go back real quick, this this bullet 1 on page replacement, this prevent overallocation of memory by modifying page fault service routine to include page replacement. Okay, so that's just saying when we go into this page fault routine, have some way of deciding, of being able to remove something from a frame and put this in its place. That makes it so that we don't, again, we don't need to have enough frames to run something because we can always use a frame that's being used by something else by replacing it. Okay? And by reducing the amount that it takes, we are going to affect our number of effective access time. Okay? But we're adding new logic here into this, what happens when a page fault occurs. We need to decide where are we going to put it, what frame we're going to put it in. Okay? So they're just showing us here this idea of when we go to our page table to look up a frame, right, we'll occasionally have page faults. A page fault is when you go to your page table and you have a little invalid entry for the page that you're trying to look up, right? Does everybody remember the valid-invalid bit? The idea that this is kind of saying, yes, it's your page, but no, it's not in memory. Because normally there should be a number here, right? A frame number. This valid-invalid bit says, yes, I have a frame number for you, or no, I don't. We need to load it. So they're saying here that they have a, they get to an instruction where they need to load this, they need to load frame page 1. So if you go to the table, you'll notice that that should be the next entry, shouldn't it? Well, they get to an invalid and they need to load it into a particular frame, right? And they need to decide what they're going to kick out because they're full. So what do they have here? I think B is going to get kicked out. I think that's what they're doing. Is B used to be here, they kick it out, they set it invalid, and then they load up the frame, the page that process 1 was looking for in its place. Okay? Because we don't have anywhere to put it. So we need to pick something to boot out. They chose this particular page from the other process. Now, the real question is, which ones do we boot out? So we're going to look at different page replacement algorithms so that we can decide who this victim frame is. Okay? What they're saying is, if there's a free frame, you can use it. That's the best, right? If you don't have to kick anything out, because if you kick something out, chances are there's a possibility that you might need to load it again, right? So a free frame is always best. But if there is no free frame, we need to have a way of choosing which of these pages are we going to kick out to free a frame, and then we can bring in the new one and then restart the instruction. Okay? So Let's take a quick break, and then we will talk about a few different algorithms. There's just a few, and we're going to see kind of how they compare. So let's take about 5 minutes.
Maybe you say free frame. I think that's
Freeze frame.
that's what I was better than saying.
That's old school.
What is the phone? Actually, one more outside the room.
Should we open the windows?
Oh, that's like in the hallway.
I don't know why it's cold here. Thermodynamics. Maybe there's more brain energy going on in the hall. Maybe there's more like thinking going on. This room's particularly cold. Oh, if that were true, it'd be warmer in here. I got nothing but the cool stuff coming out. You know that's true. Yeah. I think we're gonna have one on the next two chapters. I gotta look at some of the questions for the next chapter, the protection chapter. I'll start with the preliminary stuff here. Okay, we're going to be looking at different page replacement algorithms. Okay, so in order to look at before you start looking at any algorithms, you really need to decide what makes one better than the other, right? If you're going to be comparing them. So we've already run across a pretty good metric for how good a page replacement algorithm is, and that would be one that reduces how often we page fault, because we know that this is what really impacts performance of our page replacement system, right? It's the number that's really that's by this huge number compared to regular memory access. Okay, so what we want to do is we want to reduce the page fault rate. Okay, so in order to compare algorithms fairly, though, okay, what we're going to do is we'll compare how algorithms perform given the same sequence of page replacements that are or pages that are necessary. So what they're showing us here is what they're calling a reference string. All a reference string is my program runs along and uses these pages in order. Okay? So comparing two algorithms, you'd see how each of them performs. In other words, how often they page fault, okay, given this sequence of pages and given the same number of frames. Okay? One algorithm will be better than the other based on whoever has the lowest page fault rate, right? And you should be able to see that running them through different kind of classes of reference strings could drastically affect how the performance is overall of these page replacement algorithms. Some page replacement algorithms might be better at some types of reference strings, in other words, page sequences, than others. Okay, some may be better, overall average, but some, might be better in particular cases. Some might be bad all around, right? The ones that are bad all around probably won't show up in your books. Okay, so the idea is this is how we compare different algorithms. Okay, so here they're showing us just a comparison between the number of page faults and the number of frames. You'll notice that it's pretty intuitive that our page faults will go down the more frames we have. Why? Because we won't have to replace as many pages and potentially kick out pages that we might revisit. Okay, the more frames we have, the more simultaneous pages we can have in memory, also meaning the fewer pages that we have to kick out. Okay? How many frames?
Yeah, what does that mean? Number of frames is in?
Oh, I don't know what this scale is, but typically, like the Pentium, like Intel Pentium style architectures, they have 4K pages, but these days they have a gig of memory in them. So a gig of memory divided by 4K is how many frames you have. A lot, right? So, but I mean, I don't know what their scale is. What they're kind of just showing you, though, is that this relationship, first of all, it goes down, which is obvious. Like the more frames you have, the more memory you have, the less you'll have to replace. But also that it levels off. Notice that you get to a point where adding more frames doesn't necessarily help you. In other words, these different algorithms can give you something approaching the ideal number of frames. Okay? So this is number of page faults versus the number of frames. Okay? So, first algorithm, as with most things that we look at, is something simple, right? So we see first in, first out. Okay? So, what do you think this algorithm is? What is our algorithm trying to do? What is our algorithm solving? That's the first thing we need to know before we look at any algorithm, is what is the algorithm trying to do? What's that?
To have less page faults.
No, that's our metric, having fewer page faults. What is the algorithm doing, though? Less page faults doing what? That's our metric. The number of page faults is our metric. It's how we measure the performance of our algorithm. What is our page replacement algorithm doing? It's deciding which frame we are going to replace. Right? In other words, which frame are we going to erase what's in there so we can put something else there? Our page replacement algorithm selects a victim frame. A victim frame is the frame that we are going to boot so that we can load our new page in. So, what comes out at the end of a page replacement algorithm? A victim frame. Okay? So, here's our reference string. Okay? We have an algorithm. How do we test this algorithm? Well, we go through the reference string, right? First one. What does that mean? What's one? It's a page. I'm referencing page 1. Is page 1 in memory? No. Right, so we need to find out where to put it. Well, where should we put it? Right, we do not need to choose a victim frame because none of the frames are taken. We put it in page 1. That's one fault. Page 2. Same. We have a free frame. Put it in page 2. Page 3. Same. Quickly say same thing. We have a free frame. Right? The first 3 frames, they were all free. 1, 2, 3. Done. Page 4. Now what do? We need a victim. So, what is the victim? Why? No. Because it was the first in. It is not the most. It's not the least recently used. That's a different algorithm. It is the first in. Okay. So, what do? We choose the victim frame 1. Victim frame 1 means kick it out, put the new page in. 4. Next reference string 1. What do we do now? What? Kick out frame 2, load page 1. Okay? Next, 2. Kick out frame 3. People should be saying frame 3, right? Because we're not kicking out page 3, we're kicking out frame 3, which happens to be page 3 in this case. Okay? We kick out frame 3, the page in frame 3, load page 2 into frame 3. Next up, 5. There is no frame 4. Frame 1. We kick out frame 1, load page 5 into frame 1. That's why I wanted to make the distinction between frame and page. Go.
Why? Why did
Why what? Okay. We kick out frame 1, load page 5 into frame 1. Okay. Next one is 1. What do I do now? No. Page 1 is already in frame 2. Okay, this is a tricky part. I just did page 5 in the reference trace. Okay? I just booted out page 4 from frame 1. Okay? And I referenced page 5. Now I'm going to reference page 1 because that's the next page in the trace. But frame 1 is already in memory. It's in frame 2. So I do not count a fault for that. Next one. Page 2. It is also in memory. It's in frame 3. I do not count one for that. Page 3. Page 3 is not in memory. But which one do I boot out? Frame 2. Because that we were here in our rotation. Notice that first in, first out, you rotate through the frames. That's a good way to keep track of which one was the first in and which is supposed to be coming out. So I erased frame 2 and I put page 3 into frame 2. So now I can reference that. 4, it's not available, right? I erase frame 3, put page 4 in, reference it. Page 5, it is in memory. It's in frame 1. Okay? Everybody get that trace? You walk through, replace frames according to the algorithm, and count up the number of faults. Okay? If you change the algorithm, you change how you replace the frames, but you still step through the frames, or step through the reference string, see which frames or which pages you're referencing, and the only thing you change is how you replace the frames. But you should be able to count the faults and decide which one's better. Okay? What they're also pointing out here is notice how naive the first in, first out algorithm is. Here they've increased the number of frames to 4. They're using the same reference string. Notice they got more page faults. And then they point out this, I mean, that's a weird phenomenon, right? You added another frame. You have the same page trace, right? The same reference string. And you got more page faults. In other words, adding more frames gave you worse performance. Okay? It's no good. Okay? Because we've noticed that in general, your number of faults should go down as you add more frames. And at least this toy example, they show that that's not always the case. That's how horrible this algorithm is. Right? Is that we got worse performance giving it more resources. Okay. Oh, this is another way to look at page replacement. Notice they just walk down and replace as they go along. But they have some entries where no replacement went on. So they left a blank at those slots. This is a good way to keep track of a page trace because this whole string at the top is your reference string. We're going through these pages in this order. And what they're doing here is they're saying, when I'm referencing this particular page, this is what my memory looks like. The next one, my memory looks like this. And they keep going through and they say, okay, when I reference page 0 in this trace, right, nothing's changed, so I'm not going to put a picture there. It's the same as the last one. Okay? This is going to be the hard part of looking at these algorithms, is keeping track of what your memory looks like and where you are in the trace. But you need to get good at this, okay? Because this is how you evaluate these algorithms. Okay, is being able to walk them through a page trace and count the faults. Okay? In this case, you count the faults by showing any time you have a different look at the memory, that's a fault. So if you counted up all these little blocks, that's how many faults this particular trace had. Okay, so here they're showing us a little graph of this page trace versus the number of frames available and how many faults we get. And they show we get this anomaly where you happen to pop up at number of frames 4, where you get worse performance than 3 frames. Okay, but then you kind of go back down. So you'll have these jagged things in these graphs because they're integers that you're going to have to come out in a particular way. So, you know, if on a larger example, you might have more areas where adding frames gives you worse performance. Okay. Replace the optimal algorithm is replace the page that will not be used for the longest period of time. Okay. So here, what they're showing us is going through, and then they'll replace. When they get to the point, they go through the trace 1, 2, 3, 4, 1, 2, and then they get to 5. Okay. What they're saying here is the optimal algorithm would be to look at the pages that are in your frames and kick out the one that will be used latest. So, if I'm about to put in 5, right? If I look ahead and I see, of the pages that are in memory, which one will I need the latest? I'm right here. Of pages 1, 2, 3, and 4, which one will I need the latest? 4. So, it's saying replace 4 with page 5. Kick out 4, put 5 in, right? Then you run through. When you get to 4, which page is going to be used the latest? It's really anything but 5. So we kick out 1, load 4 in, reference it, reference it. So they're saying 6 page faults only. Okay. This algorithm that they're saying is the optimal one. It's the minimum number of page faults we could possibly have. And how it works is, when you get to a point where you need to choose a frame to replace, okay? And in this, oh, I have a little pen. Sorry. Okay. In this case, in this trace, it happens at the 5. Okay, when I'm about to load page 5. So I need to make a decision. Where am I going to put page 5? So I ask my algorithm. I say, which victim frame can I clear out? Okay, and the optimal algorithm says which frame or which page in a frame will be used latest. Okay, so the pages that are in memory are 1 through 4. Okay, so of 1 through 4 at this point in the trace, which one will be used the latest? Well, the answer is 4, because if I look through the trace, 1, 2, and 3 are all used before 4. So what I do is I put the new page in 4's place. So I erase 4, put 5 in. Okay? What that ends up doing is you run through these other pages 1, 2, and 3, and I don't have to do any replacement because they're already there. Okay? When I get to 4, I do run into a problem because I do need to replace now. So which one do I replace? Well, I do the same algorithm, but there's not a lot to look at after that. The only thing I know is that 5 will be used soon. So I don't put it back where it was. I don't put it in this frame over the bottom. In this case, they just chose the first one because that's their fallback, is the first one that is not going to be used later. So what they're saying here is that on this whole trace, this number of page usage, they had 6 faults, and 6 faults is optimal. So if we have an optimal algorithm, why don't we just use that? That's the key. This algorithm depends on future knowledge. Okay? An ideal algorithm will not need to know what pages are coming up. So why do we look at this algorithm? This is the best we could do. Right? This is the best we can do. Anything that approaches the performance of this without needing future knowledge, that's a great algorithm because we can implement it. We don't need to see the future. And we know that it's close to optimal. Okay. So this is showing us another trace of running through the optimal replacement algorithm. This look furthest ahead algorithm. Okay. Least recently used is another algorithm, and this is one that often gives us decent performance. Okay, what they do is they count how many times or how often every time a page is referenced, we reset a counter to let us know that we've used it recently. Okay. And then when we get to a point where we need to choose a victim frame, we choose the one that was least recently used. Okay. In other words, the one we haven't used that very often. Okay. So actually, I shouldn't say very often, but the one that we've exactly like it says, least recently used. So what they're showing us here is going through a trace. Okay. When they get to the point of loading page 2, right, that they need to load page 2, they replace the oldest, which in this case is just like first in, first out. Okay? But you'll see that as you go on, if I go to page 0, right, and then from there I go to page 3. Page 3 I need to load, right, because it's not in memory. Okay? First in, first out, where would it have put page 3? Right, so frame 1. So frame 0, frame 1. It would have put it here. Why? Because we just used this one, so we go to the next one. Where does LRU put it? Puts it down here in frame 2. Why is that? Well, because 0 was recently used. Right here. Or in the step right before us. So we don't want to replace that. 2 was just loaded. The least recently used was frame 2. Page 1 sitting in frame 2. So we replace that one. Okay? And, if you count up these faults, okay, you'll notice that it's pretty good. Okay? And they're just showing us some other ways of keeping track of the of which one is the least recently used. Like here they're saying use a stack implementation, okay, where you keep the page numbers in there, and as you use them you can just pull them out of the stack, not pop them like you normally would. You just pull them out and then put it on top, because that'll keep everything fresh is stuff that you've pushed into the top, and then the thing at the bottom will be your least recently used. Okay, so they're showing us a stack of as they go through the trace, how you can decide which page to replace. Okay, these are implementation notes of LRU, either using a counter, or using a stack. These are different ways of keeping track of the least recently used page. Okay. Here they're saying LRU approximation algorithms, just because, again, these replacements are happening every time we page fault, which, is going to be relative. I mean, hopefully it's a small number, but it has to happen. So doing some of these exact implementations of LRU might be too costly. In other words, doing that calculation at the time of having to replace a page might take too long. So they're saying that you can do some things like LRU approximation. In other words, kind of like least recently used, but maybe not exactly. So they have some idea of like just using a bit, and you just find one that's set to 0 as opposed to 1. In other words, something that you just loaded will be 0, and anything that you've just referenced will be 1. So you find one with 0 if it exists. Okay, but something having a 1 kind of is a bit of a hint that it's been used. Okay. Second chance, you need a reference bit. If page to be replaced, as reference bit 1, then you set it to 0, leave the page in memory, and replace the next page. Okay? So what they're saying is that if I was about to replace you, and you have a bit that says that you've been used, I won't replace you, but I'm going to set your bit to 0. Okay? That means that you better get referenced soon so you can switch your bit back to 1. Otherwise, I can choose you because your bit's 0. So that's why they're calling it a second chance algorithm, which is like least recently used. Does everybody get this idea of second chance? Everybody starts off 0. When I load you into memory, you're 0. Okay? But I have referenced you, right? Because I loaded you into memory. Right? So I might have done some stuff, but you start off 0. Now, if I come back to you and start referencing you, I'll flip your bit to 1, saying that I just used you. Okay? Now, if I get to a point where I need to kick a frame out, in second chance, I'll go through my list, and I might check you and say, hey, I want to replace you, but I notice your bit is 1. Okay? So what I will do is I will switch your bit to 0, and I won't replace you now. I'll go to the next guy. Okay? And hopefully he'll have a bit that's 0, but he might not, so I might flip him and flip him. So now you're back at 0. Okay? And let's say I found someone else to replace, and I've went on. Okay? If I have to replace and I come back to you and your bit's 0, I'll replace you. Okay? This was your second chance, but you didn't get used, so I'm going to boot you out. But if you were referenced recently, they would have set your bit to 1. So then when I come back to you, you're 1, so I'll switch you to 0 and go on. So you have 2 chances to not get booted out every time. In other words, I have to pick you twice in order to boot you out. Otherwise, you can stay in because you keep getting that bit toggled, which means you're being used often and recently. Do you see how that's not exactly least recently used? But it's kind of like it, because the more often you get referenced, the more times your bit will be flipped over to 1. Okay? Why is this better than, why do we like this? Well, because it's simple. It's just a single bit and a simple algorithm that we could potentially, implement so that we can do it so often as page replacement. Okay? All right. Next time we're going to spend a little bit more time on this in the next class, but I do want to move on to protection. I don't want to spend all of the next class on this, but I just want to at least go through a couple algorithms so you can see the page traces. Those are very, very important. But take a look in your books at some of the other algorithms that they bring up, and then we'll talk a little bit more briefly about this last part next class. But I do want to move on to protection next class. Okay? All right. Oh, also, project ideas, start posting them up or sending them to me. Otherwise, I'm going to assign it. I'm going to assign at least coming up with an idea. And if you don't come up with that, then I'll assign a project. Does everybody understand what I mean by that? I will assign you having to submit to me some ideas. That should be insulting for me having to assign to you getting ready for something that is a big part of your grade. So if I assign it to the class, it should be taken as an insult. Send me ideas anyway. Anything related to operating systems.
We can research say how Windows does something or.
Sure. Related to, I don't want to know how Windows does, I don't know, like INI files. That's for registry or something's no good. But how Windows does something that's theoretically interesting in operating systems. So something more along the lines of how does Windows do threading as opposed to how does Windows.
Or like you can compare two operating systems, right?
Sure.
The attachment file and HTML turning on the website didn't work in my home when I was getting the computer lab.
Okay.
So I emailed you the homework and the work email address.
Okay. I'll look for it. Just make sure it didn't spam.